Hey, this is Leach with Simpson Math, and in this video, we will be talking about the definition of our three main conic sections: parabolas, ellipses, and hyperbolas. I'm in a program called GeoGebra. You can access it online, geogebra.org. You can also find in the link below. There's an iPad version and a phone version, and also just on the website, you can also just download the application to your desktop if you'd like, or just watch and follow along. It's a little bit more sophisticated than Desmos, but they are similar in some respects. All right, so I'm going to first start with the parabola. There is a feature for conic sections. I'm going to select parabola, and it's going to tell me to select a point and then the directrix. The point's the focus and the line's the directrix, but I don't have a line, so I'm going to have to create one. So I'm going to undo that. I'm going to first graph a line. So I'm going to go to the line tool and pick a line. And I'm going to do a roughly horizontal line. Actually, that's exactly horizontal, yay. And with this line, that's going to be my directrix. And then I'm going to add a point. Let's put a point for my focus to be there at -1, 1. And then I'm going to graph my parabola. So now I'm going to select the parabola tool. I'm going to tap the point for the focus, and then tap the line for the directrix. And there we have it. It's created this parabola. Now, what's nice about this, I'm going to switch to the move tool. If I was to move this line around, or move my, move the focus around that point, or move my directrix around, the parabola moves along with it. So let me put this back to where it was. There's nothing special about those points that I had it, it's just where I had it. Okay, so what is special about this point and this line? So there's this line that's underneath the parabola called a directrix, and then there's a point that's in this kind of, it's not a center, but like nestled in with the parabola that's called the focus. So what's special about this particular function, actually I'm going to screenshot this so I can write on this, so give me 1 sec. What's special about parabolas is that it has some interesting geometry. Imagine that something was coming in, it was to hit the parabola on that side. It will then perfectly reflect over and will go into the focus. Additionally, if you're at the focus and you shoot something out towards the parabola, it will then bounce and ricochet out in terms of parallel lines. So if things come in parallel to it, it then reflects and goes into the focus. So this is nice because for a lot of reasons we use flashlights. Flashlights or car lights or floodlights. All of these where we have this column of light that comes out from those bulbs. They use parabolic dishes. So we have the light that sits at the focus. It sits right here at the focus. Light goes out in all directions. All the light that hits that parabolic mirror will then shoot straight out in a column. Also, satellite dishes. So satellite dishes, from space, the information gets beamed down. Basically, you can imagine basically at parallel lines. As long as it hits anywhere on the dish of the parabola, it'll then bounce into the focus, and at that focus is where the receiver for that satellite dish is. So parabolas have a lot of practical uses. All right, now the definition of parabolas deals with the distance from the focus to the parabola and the parabola to the directrix. All right, so I'm gonna add a point on the line that can be moved. I'm just gonna add a point and tap somewhere on my parabola. So now I have a point that I can move around. And then I'm going to make a line segment go from the focus to this point. So now when I move around, now when I move around this point, notice I have this point G that follows along that line segment, or that point. All right, and then I'm going to construct a perpendicular line. So there's this set of tools that's a perpendicular line. So I can go from D to this line. So there's that perpendicular line. All right, I'm going to add a point at that intersection. So that way I can now make a line segment from D to E. And I'm going to turn off that perpendicular line because I just want to see that line segment. And just to show you that it is a right angle, I'm going to choose an angle tool and measure angle DEA to be that 90-degree right angle. All right, so when this gives me, little technical note, I can make that angle always refer to 90 degrees. All right, there we go. So now when I move around, this point is always referencing that 90 degrees. There we go. All right, so what's special about this measurement? Let me actually measure this line segment CD and DE. There's a measurement tool somewhere. I always lose this thing. There it is. Distance or length. Measure G, and then let me also measure that line segment. So what is special about parabolas is that wherever the point on the parabola is that the distance from the focus to the point on the parabola is going to be equal to the distance from the point on the parabola to the down to the directrix, and that it's the perpendicular distance from the parabola down to the directrix. So there you have it. There's our formal definition of a parabola, that there is some point. If you give me a point, you give me a line, there's a parabola that can be formed from that point and line where there's the same distance from the point to the parabola, and the parabola perpendicular down to the directrix forms the parabola. All right, now let's take a look at, I'm going to clear all this, and we'll take a look at the ellipse. All right, for the ellipse, it just asks us to put two dots that are, each of them is a focus, so collectively plural form of focus is foci. So we're going to put our two dots for our focus. Let's put one here and one here, and then I'll put a third dot, which is going to be on the ellipse itself. I can actually move around this points. I'm going to put this just on one of our nice numbers, if possible. So here we have one at, let's do 4, 2. So I have 4, -2, and -5, -2 for the foci of the ellipse. And then point C is then a point that is on the ellipse. So let's say that I want this ellipse to go through the point 2, 3. There we go. So here is the ellipse that has those 2 points as a focus, and then point C is on the ellipse. I'm going to add another point, this point that I can move around freely. So this is point D. I can move point D around freely without changing the parabola. If I try to move C, then the ellipse, then the ellipse changes. And so I'm going to draw line segments from the focus to D. All right, so we have these 2 line segments drawn. And notice again, if I move around D, these line segments are going to follow D. And there's a special relationship between these line segments. So this program labeled them F and G. That's fine by me. All right, down here in this input line, I'm going to type in F plus G. So on my keyboard, F, and then plus G, and then enter. So notice here it says the F plus G is 13.99. All right, let's move D around a little bit. So my distance changed. I can even add the measurements so we can see those. So we can see the measurements of both of these. And notice that as I move them around, the distance changes, but look at the total distance. When I add F and G together, notice it is 13.99. Just to show you that this is a bug, I'm going to move C to a different point. I'm going to move it to be 2, 2. Now F and G add together to be 12.53. When I move the point around, notice what we get. It's 12.53 regardless. So this is what is special about the ellipse, is that the distance from the focus to a point on the ellipse, and then from the other focus to that same point, if I add up those 2 distances, it is going to be a constant. It's going to be the same all the way around. I can move make it be a vertical ellipse, which we'll be seeing. Let me move the focus, let it snap into place. There you go. And so here, so we move this around, 10.06, it's the same. All right, so that's the definition of our ellipse, is that the distance from the focus to the point on the ellipse and then the other focus to that same point, you add them up, it's the same for all points. All right, let me show you the hyperbola. All right, lastly, let's take a look at the hyperbola. So I'm going to pick the hyperbola function. It wants me to put 2 points for my foci, and then a third point that is going to be on the hyperbola. So there we have it. We have a focus at 3, 1, another focus at negative 1, 1, and then a point on the parabola is 2, 3. I can move this point around so that we can put this wherever I want, and we'll get my have my hyperbola. All right, so there we go. I'm going to add a point to move around on the hyperbola, just like with the ellipse. So there's this D, I can move it around. If I want it to be over on this left part, I can do that. All right, and I'm going to put a line segment from each focus to D. And again, I can move it around and they follow. Okay, and let's put up my measurements so we can see those measurements. And this time, instead of the sum of these, F and G, I'm going to do the difference of them. And actually, I'm going to do, let's do the difference of them. So F minus G, that's an I, F minus G. All right, so F minus G here, it's a negative 2. And notice that whenever I move D all along this hyperbola, my distance is staying at negative 2. I don't know what that B is. Let me get rid of that. There we go. And then if I pop over to the left side, notice that it's a difference of positive 2. So it's negative 2 over here and positive 2 over here. Let's consider distance to be positive. So I'm going to actually edit this distance to be the absolute value of F minus G. So I have a function right here. Somewhere I have absolute value. Let's find it. There it is. Absolute value of F minus G. So now let's move this around. So it's a 2 over here, and on the left side it's a 2. So notice it's a constant. It's the same difference regardless of what point we use. If I move this focus around, let's put the focus here, and let's keep C even in the same spot. So here, this time when I move D around, it also has a difference of 2. Yikes. Let's put C way up here, right? So now it has a difference of 3.1. So regardless of which X and Y point I put, the distance from one focus to the point and the other focus to the point, its difference is 3.1. All right, so let's summarize this. So the definition of my 3 conic sections, we have a focus and a directrix. These are non-graphed elements. I know you saw them on my graph, but they're not a part of the graph. They are non-graphed elements. The focus is just a point. Plural form of focus is foci. And then the directrix is this line. So for our parabola, if I have this distance D from the focus to any point is equal to the perpendicular distance from that point to the directrix. So I could have picked this point over here. It would have been from there to there and there to there. Those would have been the same. All right, for my ellipse, it's the sum of all the distances. So this distance plus that distance for all points in the ellipse are the same. And then it's the difference for the hyperbola. So when I go from this distance minus that distance, for every single point, this distance minus that distance, they're all going to have the same distance. I notice I'm defining the distance to be the absolute value of those two. I forgot to mention a minute ago about some applications about the ellipses. One big thing about ellipses is that we have elliptical motion, elliptical orbits. The Earth revolves around the sun, not in a circle, but it's actually an elliptical orbit. And there's a little bit of an extreme ellipse, but our sun is at one of the foci of the ellipse, and then the Earth and on all the planetary bodies travel around that. Same thing with the moon traveling around Earth. It's not quite circular; it's slightly elliptical, and we're off center, and we're sitting at one of those ellipses. And also another interesting application of ellipses is there's like one in Washington D.C., one in Chicago. There's other places that have these like whispering rooms where someone might be standing at one focus, and there is this elliptical dome that you're sitting in, that you're standing under, and you could whisper, and your sound bounces all around, and will then land and all come back in to where your friend is at the focus of the other. So wherever you whisper, it'll bounce and then go to your friend. So it'll go bounce. Right, so that's one of the applications. Another application of the this ellipse. Interesting thing about hyperbolas. Just one note with this is, so anytime you see cones and they get intersected, often than not, you're probably seeing a hyperbola. So like if you have a lamp and it's close to a wall, that that cut cone of light is a hyperbola. The sonic boom, that cone that travels out from the sonic boom when it intersects and hits the earth, that mainly is a hyperbola. All right, so that's some applications of the hyperbolas. All right, so there you have it. There's our definitions of the three conic sections. In the following videos, we'll be looking at a much more deeper into the parabolas, ellipse, and hyperbolas. We'll be completing the square. We'll be doing a lot of algebraic manipulations, and then also ultimately graphing them. So I hope this introduction will serve you well in those following videos. All right, take care. We'll see you then.